This story starts the fall of my sophomore year when I attended the Highlands Field Site that's sponsored by UNC's Institute for the Environment at the Highlands Biological Station, located in Western North Carolina. And while there, my cohort and I participated in our capstone research project that investigated microplastic concentrations and dynamics in the headwater streams of the southern Appalachian Mountains. Now, this project was led by Jason Ludd, who's the assistant director of the biological station up there, and Dr. Jody Miller, who's affiliated with the nearby Western Carolina University. So, to start, I'm sure that many of you in this room have heard of microplastics. They are a dominating news material these days. But just a quick definition before I move on. Microplastics are plastic particles that range in size from 1 micrometer to 5 millimeters in length. And they can be classified in a multitude of different ways in terms of coloration, size, and texture. And I also want to emphasize how exactly microplastics are formed. The ultimate answer to this is that they are simply degraded in our environment through weathering processes. And global estimates indicate that only 9% of plastics produced have ever been effectively recycled, indicating that there is a significant proportion of plastic left in our environment that can be degraded down into these microplastics and infiltrate our natural world. And to link this to freshwater systems, the primary means of transport of microplastics into our aquatic systems are in 3 different ways. Primarily through direct littering, through surface runoff, and wastewater effluent. Wastewater effluent is simply just the discharge of water from wastewater treatment plants. And several studies have shown that wastewater treatment plants are not effective in filtering out microplastics from wastewater. So, microplastics can be transported into our aquatic systems and pose several serious threats to our aquatic biota. There are numerous health concerns that are directly connected to microplastic exposure, including toxic, physiological, and molecular impacts on both humans and aquatic biota. So with these concerns in mind, despite the fact that the harmful nature of microplastics and exactly how ubiquitous they are in our environment is well known in the scientific community, as of 2018, less than 4% of microplastic research focused on freshwater systems. Now, this was a pretty staggering fact for my PIs and our team, and led them to start this project and attempt to begin building up freshwater microplastic sampling methods in the Southeast region. So that leads me to our study site, which is on the Chattooga River. The Chattooga River is located in Western North Carolina and has a wild and scenic designation, indicating that it is in pretty pristine condition and is surrounded by primarily forested terrain, and is located in the southern Appalachian Mountain Range. And many say that the southern Appalachian Mountains serve as the water towers for the Southeast. So any ecological impacts to the Chattooga River in this watershed can have a trickle-down effect on the entire Southeast region. So now that we had our study site in mind, we then sought to lay out our study objectives. There were 3 main goals of this study. The first was to simply sample this stream and see if we could even collect microplastics. And we chose to sample before and during storm events in order to isolate rainfall and high storm flow events as potential sources of microplastics. Our other goal was to quantify and characterize any detected microplastics and begin building up this knowledge base and methodology for microplastic sampling in freshwater systems. And lastly, we sought to build a secondary analysis method using Raman spectroscopy to identify the chemical composition of any particles that we did collect and verify if they were in fact plastics. So we sampled, we quantified, and then we verified. And now to walk you through our methods really quickly. We started out by simply conducting our topographic and hydrologic surveys at our 2 stream sites. We had 2 sampling sites, one above the local wastewater treatment plant on the Chattooga River and one below the treatment plant. And we collected regular discharge measurements in order to relate those to our microplastic concentrations. And there's a lovely picture of us and our waders out in the stream. And this map here is just to show you all that we were working in forested terrain in a pretty pristine environment. The next step was we collected our water samples before and during storm events using ISCO water samplers. We did do a bit of storm chasing where we had to watch satellites to look for storms coming through the area with significant enough rainfall in order to go out and program our ISCOs to collect our samples at the predetermined intervals. And we also deployed atmospheric deposition buckets, which were simply just rainwater collection buckets. And we would remove the lids during our storms in order to collect rainwater samples in addition to our river samples. Once we had our samples, we then went to go filter them using a vacuum filtration system in our clean and sterilized lab environment, and then analyzed our filtered papers under microscopes to see if we could identify any potential microplastic particles. And the last step of this, as I said before, was to use Raman spectroscopy at our partner lab at Virginia Tech. We utilized the Raman spectrometer to verify if what we found were in fact plastic particles. So the results of this, these two figures here were our primary figures from our cohort. These figures relate discharge to microplastic concentration. The blue dashed line shows our storm flow, and the orange lines show our calculated microplastic concentrations. And in both of these figures, you can see a slight peak in microplastic particle concentration right before the peak discharge, which led us to hypothesize about a sort of first flush phenomenon. So maybe this peak storm flow is coming through our rivers and flushing out plastic particles from groundwater and the riverbank sediments. However, we did run into several issues with breaks in our data and contamination, which I will touch on later, which did cause us to lean away from this hypothesis. And this table just simply shows our calculated accumulation rates of plastic particles in our rainwater collection buckets. So our key findings were first that we did not find a significant relationship between discharge and microplastic particle concentration, therefore leading us to lean away from that first flush phenomenon hypothesis and then look more towards our atmospheric deposition results. We did find similarities between our atmospheric deposition plastic particle rates, indicating that there is the potential atmospheric circulation of microplastic particles. Plastic particles could be evaporated up into our atmosphere and then precipitated down into our aquatic environments, which is a significant area of concern. Our third result was that we also found high contamination levels detected in the Chattooga River, which was another area of concern, considering that this is a wild and scenic designated river and a pretty pristine area. And lastly, we were successful in confirming majority of our year's plastic particles as anthropogenic microparticles using Raman spectroscopy. I use the term anthropogenic microparticle because the spectroscopy revealed that a lot of the particles we identified were other anthropogenic materials such as paint chips and synthetic fibers, which also have toxic effects when released into aquatic systems. So these were our key findings, and I quickly want to touch on the limitations of this study, the primary one being microplastic contamination during our sampling and analysis. We live in a world where plastic has infiltrated nearly every material that we use, and so when sampling, one brush of a hand on a synthetic fiber-made shirt can release particles onto your filter papers. And we did take significant steps to help mitigate this. We wore brightly dyed purple lab coats, and this picture here shows a purple fiber from our lab coats on one of our filter papers indicating contamination. We installed air filters, and we regularly cleaned and sterilized our lab, and I just want to emphasize that with any microplastic study, considering contamination is one of the most important steps for this study, and we are still working to deal with this contamination issue. So despite these limitations, we were successful in identifying contamination in the Chattooga River, therefore leading us to emphasize that this is a unique threat to Southern Appalachians, considering it is a biodiversity hotspot for this region, and therefore it should continue to be monitored closely, and it is continuing to be monitored closely for future management efforts. So these are our main points, and I quickly want to acknowledge everyone who has played a role in this project, specifically to Jason Love and Jerry Miller, who brought this project to life, and to the entire Highlands Biological Station staff, and the now 3 Highlands cohorts who have continued this research and are continuing this research. And Jason wanted me to announce that we've been asked to submit a publication to the Microplastics Journal this summer, so if you're interested, you can keep an eye out for that. And that is all I have for you today. Thank you.